let's solve some more questions from the chapter thermal stresses. The question says that a steel cube with all faces free to deform, okay, has a Young's modulus E, Poisson's ratio nu, coefficient of thermal expansion alpha. The pressure developed within the cube when it is subjected to a uniform increase in temperature delta T. Okay, so the steel cube is free to deform, okay, there is no restriction on it, and when it is subjected to a uniform increase in temperature delta T, as a result there will be strain in the cube, but the stress will be zero because the steel cube is free to deform. So the answer will be A option. The next question is a circular metallic rod of length 250 mm is placed between two rigid immovable walls. So these are rigid immovable walls. The rod is in perfect contact with this wall and there is a gap of 0.2 mm between the second wall and the rod. If the temperature of the rod is increased by 200 degrees Celsius, the axial stress developed in the rod is, okay, so I have to find the axial stress, and the Young's modulus of the material is given, that is 200 gigapascal, and the coefficient of thermal expansion is 10 raised to the power minus 5 per degree Celsius. Okay, now let's analyze this question. If this is first wall, this is second wall, okay, if this second wall was not present and we have raised the temperature of the rod by 200 degrees Celsius, what would have been the change in length in the rod? So if this second wall was not present, okay, so the value would have been equal to L alpha delta T. This would have been the change in length if this second wall was not present, okay, and this value is equal to L is 250 mm into this alpha is what, 10 raised to the power minus 5, and delta T, so this is in mm, so this delta L will get in mm and its value is equal to, I guess it will be 0.5 mm. Okay, now see here that 0.2 mm length of the rod is free to expand, and after it expands to 0.2 mm, the restriction by the wall starts. So actually the restricted elongation is 0.3 mm, okay, 0.5 minus 0.2 mm, that is 0.3 mm, and this restricted elongation will actually provide the axial stress in the rod, okay, because for 0.2 mm there will be no strain because the rod will be free to deform, and after this 0.2 mm there will be restricted elongation. I mean the rod will not elongate further because the wall is present, and the stress in the rod will be due to this restricted elongation. So strain will be equal to restricted elongation upon original length, restricted elongation upon original length, and this becomes equal to 0.3 upon 250. Okay, so this is strain, and that implies stress will be equal to epsilon into E. So epsilon is 0.3 into 250 into, and the Young's modulus is 200 gigapascal, that is 200 into 10 to the power 3 megapascal. So we'll be getting the stress in megapascal. Okay, here we have to fill the answer in megapascal. So solve it. The answer will be 240 megapascal. Okay, so 240 will be your answer. Okay, let's move on to the next question. An initially stress-free massless elastic beam of length L and a circular cross section with diameter D, where D is much less than L, is held between two walls as shown. Okay, the beam has Young's modulus E and a coefficient of thermal expansion alpha. I guess the question is not complete. Okay, the question is actually that if this beam is slowly and uniformly heated, the temperature rise required to cause the beam to buckle is proportional to. Okay, so I'll repeat the question. Question is that if the beam is slowly and uniformly heated, the temperature rise required to cause the beam to buckle is proportional to, and the options are it is proportional to d, or it is proportional to d square, or to d cube, or to d raised to power 4. Okay, so we have to find the temperature rise is proportional to whatever are the options. Okay, so we have been given Young's modulus, that is E, and coefficient of thermal expansion alpha, and we know that at the condition of buckling, the buckling load is equal to pi square EI minimum by LE square. Okay, so LE is effective length, I is the moment of inertia, minimum moment of inertia, I minimum is Young's modulus. Okay, so this is the buckling load. Okay, now this rod has been heated with the rise in temperature, let it be T. Okay, so the thermal stress will be equal to E alpha delta T. This is delta T is rise in temperature. Okay, so this rod has been heated and delta T is the rise in temperature. So the thermal stress which will be developed in the rod is E alpha delta T. And can I find the force from this expression? Yes, because the force in this rod due to rise in temperature will be equal to sigma into the area of the circular rod, area of cross section. So this is E alpha delta T into pi by 4 d square. Okay, and I know that the buckling load will be equal to the force or the reaction applied by the wall when the temperature is increased by delta T. Okay, this is F, this is F. Okay, so equate both of them. Pi square EI minimum by LE square is equal to E alpha delta T into pi by 4 d square. Okay, but wait a minute, I minimum is P square E pi by 64 d raised to power 4 by LE square is equal to E alpha delta T into pi by 4 d square. So what we have to find? We have to find the relation between delta T and the diameter. Okay, so this gets cancelled out, d square. Okay, all the other terms are constant, so delta T is directly proportional to d square. Okay, so option B is our answer. Okay, next question. The next question is, a cantilever beam of length L and a flexural modulus EI is subjected to a point load P at the free end. Okay, so this is a cantilever beam and there's a load P at the free end. Okay, the elastic strain energy stored in the beam due to bending neglecting transverse shear. Okay, so we have to find the elastic strain energy in the beam only due to bending in this case. Okay, and we know that let the cross section XX at a distance x from the free end, strain energy is actually written by m square xx dx by 2ei, where mxx is the moment due to this load at the cross section xx. Okay, so the moment due to this load at cross section is p into x, simple. So put this p into x here. So u is px square dx. Dx is the small element that I have taken here on 2ei, and integrated from 0 to L because the length of the beam is L. Okay, so integrated from 0 to L. So this is U is equal to 0 to L p square x square dx by 2ei, which is equal to p square x cube by 6ei, 0 to L. So the strain energy, the elastic strain energy stored in the beam due to bending is equal to p square L cube by 6ei. Okay, very basic case to find the elastic strain energy stored. Okay, so let's move on to the next question. Okay, the next question is, a steel bar is held between two fixed supports as shown in the figure, and it is subjected to an increase of temperature which is equal to 100 degrees Celsius. If the coefficient of thermal expansion and Young's modulus is given as this respectively, the magnitude of thermal stress. Okay, a very simple question again. The question is directly based on the formula. The magnitude of thermal stress is equal to E alpha delta T when a steel bar is held between, when a bar is held between two fixed supports and it is subjected to an increase in temperature by delta T. So thermal stress is equal to E alpha delta T. E is Young's modulus, alpha is the coefficient of thermal expansion, and delta T is the increase in temperature. Okay, so E, that is 200 gigapascal. I have to find the stress in megapascal. So 200 into 10 raised to the power 6 megapascal into alpha is 11 into 10 to the power minus 6 per degree Celsius into delta T is 100 degrees Celsius. Okay, so this gives me the magnitude of thermal stress in megapascal, and the value will be equal to 220 megapascal. Okay, this is P megapascal. Okay, so sigma is 220 megapascal sigma thermal. Okay. Thank you.